Hello, I'm Aiden. I'm the president of the Competitive Programming Club, if you don't already know me. And this is a video replacement for the first meeting's recording, because unfortunately the Zoom audio did not survive, which it's always something with the Zoom, but hopefully that won't happen again. So first of all, let's talk about the problem that we solved at the Student Involvement Fair, the X and Y junctions problem. So essentially, if you haven't seen the problem yet, we're given some number of X and Y junctions, which are these little X's and Y's that can be bent and stretched as much as you'd like, and we can connect them end to end. That's with these black connection points, for example, and we want to determine, given some number of either of these two junctions, or given some number of both of the two junctions, is it possible to connect them together without leaving a dead end, such as in the bottom right, where we have a dead end of this, or we have a dead end right here. So we're trying to figure out a procedure or some kind of formula to help us determine, given any number of x's and y's, is it possible to connect them all together without a dead end. So if you haven't tried this yet, then I guess you can pause the video if you want to. So I'm going to take this top left diagram as an example to describe my solution to this problem, or how I would come up with that solution, I suppose. So one thing to notice is that if we look at any of these connection points in particular, so for example, this one that's highlighted, each one of those connection points has two of these little, I'm going to call them branches, that are connected together, which is kind of an obvious statement, like two things are connected together, which means that there are, two things that are part of the connection. But what we can infer from that is that if we look at all the connection points over the entire diagram, then we can pair up each of these branches based on the connection point. And so what that means is if we have something like this where all of them are connected together and there aren't any dead ends, then the total number of these branches has to be even, because they have to be in pairs, grouped together by these connection points. So the total number of branches has to be even. That's our first observation. Second observation is that because an x has 4 branches, which is an even number already, the number of x's doesn't actually change anything about the connectability of the junctions. So because an x has an even number, we can always just connect the x's branches together, connect them, in a loop if we wanted to. That's not done in this case, but we could do that. We could just connect them together in a loop. And so the x's don't actually change anything about whether we're able to connect them all together without leaving a dead end. So we can effectively ignore the number of x's. And so as a consequence, the number of y's is the only thing that matter. And in particular, the number of y's has to be even. If there's only one y, for example, you're always going to have one left over. You can connect two of them together, but you can have one left over. And the reason we need an even number of y's is because if we had an odd number of y's, each of the y's have an odd number of branches, and an odd number times an odd number is still odd. So we'd have an odd total number of branches, even including the x's, which don't change the parity. And that means there would always be a dead end if we had an odd number of y's. So we need an even number of y's to connect them together to form a closed loop. So to give you a rough idea of what an actual competitive programming problem looks like, this is a much more abstracted version. I'll actually go to the problem that this was based off of, which is, oh, spoilers, don't look at that, which is Railroad, the Kattis problem called Railroad. Officially it's called Railroad 2. But I'm not going to go through this whole problem because it's kind of wordy, as most competitive problems tend to be, But if you do read it, which I encourage you to, you will be able to see that it's actually semantically equivalent to the one that I described earlier. So a competitive programming typically has a description like this, and it has a description of the input and output, which are pretty precisely defined. You can see that they're 2 integers and they're in this exact range. And it also describes the output pretty precisely. It needs to be the word possible or the word impossible. And we're given test cases. So these test cases are actually less descriptive than test cases that we gave you because they don't show you how they connect together. They just tell you that it is possible. And that's also pretty standard. They're not going to give you all the information. Sometimes if it's a especially difficult problem, they might explain how the test cases work, but not always. So I wrote a solution in Java because that's a fairly common language to use, considering most of the CSE classes use Java and teach Java. And this is a Java version of the algorithm that I just described to you earlier, where we know it's possible if and only if the number of y's is even, and that's how you do this in Java. You check the modulus is equal to 0. So let's try to submit this, and I'm realizing this isn't going to work again. It's happened one time already, but I'll give you an idea of what happens if you have a compile error. So in this case, we actually forgot to import something, which is a very common thing, very common mistake to make in Java, for me at least. But now this should be correct. Scanner is in the java.util package. And what the Kattis is going to do is it's going to run against a set of private test cases, which are similar to ones it provided, but they're more comprehensive. And it's going to check that that my program correctly outputs possible or impossible in the right cases. In this case it did, and so this was accepted, and we get the green check marks, which we love to see. So that was just a little bit of a taste. I'll describe to you, I'll make this pretty brief since I kind of already described to you and showed you what one looks like, but I'll describe to you what competitive programming is generally. And generally, it's just programmatic problem solving with precise inputs and outputs. The reason I added that part at the end is because programmatic problem solving itself is pretty general and can encompass a lot of things that a software engineer does. But a lot of the time, problem solving, your inputs and outputs are kind of ambiguous. So in this case, because it's a competitive setting, we need precise and unambiguous inputs and outputs. And so that's kind of what makes competitive programming different from normal software engineering. So in competitive programming, there's also some scoring requirements. That's part of the competitive part. And in order of importance, you first need your solution to be correct. And in most cases, there isn't any partial credit for this. It either works with all the test cases or it doesn't. So that's one of the most important parts, is actually figuring out how to solve the problem, even if it's not the best way to solve the problem. Just figuring out how to do it at all is step number 1. Once you do that, what you need to worry about is efficiency. And efficiency here isn't as efficient as possible, but rather efficient enough. There's usually a set amount of time that your solution can run in that is the maximum. And if it's longer than that, then that's basically as bad as being incorrect. It still won't pass. You'll get a wrong answer, or actually you'll get a time limit exceeded in that case is what it's called. But it doesn't need to be as efficient as you can physically make it, it just needs to be efficient enough. And this is because most of the efficiencies come from making an algorithm that has a better complexity, which we'll probably talk about at the next meeting. But we're focused less on very low-level efficiency details. We're not getting into the weeds of the system's programming to figure out how to make this 10% faster. It really is a question of, is the algorithm the right algorithm for the job? And once you have those two requirements, once you've actually gotten the accepted, which happens if it's both correct and efficient enough, then the next priority is to solve them quickly. And that means figuring out how to solve them quickly and also actually like physically typing them in quickly. These tend to be more relevant like at the higher level, but they are definitely considerations, and it does influence some choices on, like, for example, what language you use and what you put in your set of templates, which are basically predefined sets of code that you're allowed to have. But yeah, that stuff is mostly for the higher level, but it does come into play. So, okay, so at this point I've hopefully described to you well enough how competitive programming works, if you didn't already know that. But now I'm going to try to convince you that it is interesting and worth your time doing. So I'll get the two kind of obvious reasons out of the way first. You like competing or you like programming. So if either of those two things are interesting to you, I mean, they're in the name, so it's probably going to be something that you're going to want to do or that you'll find enjoyable. But that's not the case for everyone, which is understandable. It is a little bit of a niche hobby, but I think there are still other reasons that you might be interested. For example, you want to get a good job. It turns out that competitive programming problems are a really good way of gauging how good you are at technical abilities like using data structures and algorithms and programmatic problem solving, because they're designed that way. And so a lot of companies actually use these problems or very similarly structured problems to figure out which candidates are good at problem solving, which is in high demand, obviously, for software companies. And so doing competitive programming is kind of like a roundabout way of getting good at these types of skills. Even if you're not interested in competing, you're not interested in solving the problems as fast as possible, just solving them at all will put you in a really good position for a future career or any future programming you want to do, really. And finally, another reason you might be interested in the club is just because you enjoy spending time with and learning from other computer sciencey people. This is actually the reason that I joined the club originally. It's it's a nice place to just hang out with other people that are also interested in the same things that you are. So that's definitely a valid reason why you might want to come to CPC. So I'll go over now just a few more details about things that we do. The first thing is the sort of primary goal is ICPC and to do well in ICPC. And the way we do well, or the way we try to get our members to do well, is by giving lectures, kind of like the one I'm giving right now, although more focused on the content usually than the logistics. But we give lectures and we do practice contests. And this semester we're also doing sort of work days, which are these open office hour meetings, which I'll talk a little bit more about later. But ICPC is ultimately the main primary goal of the club. And you can see some pictures here at the 4 different stages of ICPC, which I'll talk about now. There's 4 stages corresponding to the college, regional, national, international levels of the competition. And the first one is the college level, which is known as the North American qualifiers. And so what this is a contest where we rally up all of Ohio State's competitive programmers, and we figure out which of the best, or we figure out we rank them essentially based on this contest. So the contest problems are actually given by ICPC, but our club is the one that does the sort of managing and hosting the room and all that stuff. And the format for this contest is the same as the format for all of the ICPC contests. The only thing that really varies is the difficulty. But the format is essentially teams of 3, or up to 3, solve roughly 9 to 10 to 12, something in that range, programming problems. And you're allowed to sort of go in any order you want, but you want to solve as many of them as possible and as quickly as possible. And of course, like I said earlier, they also have to be efficient enough to pass the test cases in the amount of time allotted. But that's the format of the competition, and that's the format of actually all 4 of these competitions. But if you do really well at NEQ, then you might be able to go to ECNA, which is the first regional contest, basically, for ICPC. This is the East Coast North American contest, and so this is where teams from the East Coast, some notable examples, Purdue, Waterloo University, University of Michigan, University of Toronto. So it's a pretty competitive contest, and I think it's one of the most competitive regional contests. But yeah, if you do well in NAQ, we send usually 3 teams, sometimes 4, to ECNA to compete with all these other schools. And if you happen to do well in ECNA, like these 3 gentlemen did, and have done a few times, then you can advance to the North American Championship. So I'm realizing now that the webcam is covering a lot of the text, which I apologize. I did not really think through that one, but I've attached the slides in Discord if you want to look at those and follow along. So this takes place in Orlando, Florida, and this is where schools teams all around the country come together, the best teams in the country come together and compete to try to see who advances to the next stage. We have gone to the North American Championship a few times, but it isn't easy. This team actually went twice. This is Brandon, Spencer, and Robert. And unfortunately, those 3 have all graduated last semester, so there is a pretty big opening if you're interested in trying to go to NAC. But if you happen to do well in NAC, which Ohio State, if you do well at NAC, then you might be able to go to the World Finals. As far as I know, Ohio State has only been to the World Finals 1 time, and I think this was actually before NAC was even a thing. So it was when you went straight from ECNA to the World Finals. This was back in 2016. So yeah, very difficult to get to this stage, and this is the last stage. So if you do well at the World Finals, then you win the whole thing. But yeah, quite difficult to get to this point. Again, I think this is the only Ohio State team that's ever done it, but it is possible. So aside from ICPC, we also try to do some local events at the college. One of them is the Buckeye Programming Competition, which is a kind of a mock ICPC contest, but we use our own online judge and we write our own problems, the officers of the club and various other people that are affiliated with the club. So it's more of a local competition. It's not, there are usually prizes, but it's not as high stakes. There's not really a step after it. It's just a annual competition that we do to, get people interested in the club. The other event which we usually do, which has popped up relatively recently, is the Arcade of Code. And this event is more accessible. It is still a competition, but it is a little bit more laid back, and we focus more on just doing things that are silly. The first time, so for example, the images you see here are actually Spencer and Parker, 2 of our members, that are racing to solve this competitive programming problem, which is largest prime factor, using Scratch, or at least some, Scratch knockoff. And so yeah, that's one of the parts of last year's competition, or maybe the year before. And also this was being live streamed, so kind of fun. Some other examples of things we did at this competition are we had like a code golf competition, which is shortest source code, and some other things like solve this problem without using any loops, which was interesting. But yeah, we hope to do both of these events this year at some point, but the current plan is to maybe push them to next semester, just so we can focus on ICPC stuff this semester. Now, with all of that information out of the way, I'll talk to you about a little bit more detailed, like, logistics stuff. So, this semester meetings are Thursday, from 7 to 8 p.m., mostly, in one of these two rooms. So, yeah, the only exception to the time and the date is on November 6th, which is, it's going to be 7:30 to 8:30. But we will be sure to inform you of that multiple times in large underscored, bolded, and italicized text, probably, just to make sure, everyone remembers. But usually 7 to 8 in one of these two rooms. Okay, so why are there two rooms? Well, we did two rooms, so, okay, yeah, I guess I should just talk about the schedule first. So, the reason we have two rooms is because the schedule is a little bit different this semester. We're trying a system where each month is on a little bit of a cycle. So, the first Thursday of the month is a lecture, and the last Thursday of the month is a, little mini contest that takes up the hour of the meeting. And in between those two bookends are basically work days, which are open office hours for anyone to, no battery, for anyone to do anything that they'd like, work on any problems, ask any questions. And we'll provide some problems after the lecture, but it will mostly be self-guided. And we're hoping that'll help with some of the pacing issues that people have dealt with in the past, where it can be difficult to catch up if you miss a few meetings or if you come in halfway through the semester, for example. So that also explains why we have different rooms. Emerson 311 is a really good room because it has tables where you can fit 4 to 5 people, and it's good for collaboration, which you want to encourage. Also good for the contest, where you'll be in teams, if you'd like to. And but Emerson 311 is a notoriously bad lecture room. If you've never been in that room before, the podium's right in the middle, and there's TVs. There's 8 TVs around the room. It's kind of weird. Not very good for lectures, so that's why we're doing them in 031. Hitchcock 031, which is a more traditional lecture room. Everyone's facing the same direction. That's why the difference in rooms is there. But we'll inform everyone, before the meeting, as we usually do, when and where the meeting is going to be. So if you pay attention to that, you shouldn't, you should be okay. The only exception to all this is the last day of the last meeting of the semester, December 4th, because that's the last, that's the last meeting. The meeting after that is, or the Thursday after that is during finals week, I think. So we're just going to do something chill that day. And this is also all tentative, so it's entirely possible that 2 weeks from now we just completely change the whole thing up. We're just experimenting with different things to try to fix some of the issues that we've noticed in previous semesters. All right, so I'm going to skip that slide. Someone asked about resources at the meeting on Thursday, so I just wanted to quickly go over these. This is not a comprehensive list. There's a lot of stuff, but these are good for getting started. So first of all, the club website is here. It's cpcocu.github.io. By the way, these are all links, so if you download the slides, you can click them if you want to follow along. But this is the website. We're going to try to keep this as up-to-date as possible and have as much information as is useful. It has a schedule page which has information about the time and room, which may be useful. So if you're, we'll send announcements, but if you just want to refer to this or plan for the future, you can check this page. Now, for learning competitive programming concepts, the really big thing is this book, which is called the Competitive Programmer's Handbook, and it's kind of like the canonical competitive programmer's textbook. It's very comprehensive. I haven't even read the whole thing, but it is very good for learning about fundamental competitive programming stuff. And almost every problem is going to use something in this book or some variation of something in this book. So it's a great place to start. Another thing which I haven't used very much, but I've heard good things about, is usico.guide. And this is actually intended for usico, which is a different competitive programming competition, but it's still competitive programming, so it's probably still useful. There's different things, I guess. I haven't used this very much, but it's something to check out. It also has problems, and that kind of brings us to the next part, which is getting good at competitive programming is almost completely about practicing a lot. So even though this handbook is going to help, you're probably going to spend 90% of the time doing practice problems compared to actually learning new stuff about competitive programming, because that is really just the way to get good and see, also just figure out how to implement these things, even if you already know them conceptually. So here's a set of judges that we kind of recommend. Kattis is a judge that is used, that ICPC actually uses for their contests. So the types of problems are similar. The format of the problems, I should say, are similar. Codeforces is also a good one, and it has some other nice features like tagged problems and various other things. Here's also another problem set by the creators of the book. And LeetCode is a classic. The only thing about LeetCode is that the problem format is a little bit different. You're given a function that you define instead of taking input and output, but it's not too difficult to switch between the two. Okay, and finally, if you are interested in seeing more what the ICPC contests are going to look like, this is a nice website that archives a lot of the ICPC contests. So here's NAQ, the regionals, and NAC. I'm sure World Finals are in here somewhere. But yeah, this is good for maybe not only for just practice problems, but also if you're already maybe good at competitive programming, but you want to study in a little bit more detail what the ICPC contests look like, what types of things appear on them, what the prose of the description looks like. This is a great resource for that. Okay, and then finally, just a reminder, assuming you're watching this before the state, the next meeting is this Thursday, September 4th, on Thursday from 7 to 8 p.m. in Hitchcock 031. So it will be probably mostly a lecture, just talking about some more detailed competitive programming stuff. The basics, I think, is the official name. But yeah, if you have any questions, ask in the Discord channel or DM or send an email. Any of those work. But other than that, I hope to see you on this date, or in the future, if you're watching this after this date, then the meeting after the upcoming. You know what I mean. Okay, bye.